Hello and welcome to my YouTube channel. Today I'm going to show you how we can interpret the statistics returned by the Pandas data frame. When you do data frame.describe, Pandas will give us some statistics. How we interpret that, how we can detect the outliers from those statistics is what we are going to see today. So to start with, I will write some basic Python code. It's not any huge data set or anything. This is a sample data set I'm creating. Once this is done, I will show you the mathematics behind this one. We are going to do some mathematics by hand so we understand the statistics behind this. Let's get started. So first I will import numpy as np and import pandas as pd. Let me also import a seaborn so we can plot the histogram to see the distribution of the data. Is pandas. Right, we have that one. So what I'm going to do is I will going to create a, it's not seaborn, it's seaborn. Data is equal to, I'm going to do some random ages between the range of 30 and 50, and I will take 100 data points to visualize the data. Let's say np.random.randint. The lower limit is 30, upper limit is 50, and I want 100 data points. And if we see the data here, so I got this one. Now let's load this numpy array into the pandas data frame. But that we can do df data frame is equal to pd dot data frame. I have to supply the data, which is data is equal to the data which I've got above, and columns. I will name this column as age. Right, so far so good. Now if I do df.head, I got these values here, the first the top 5 rows, and let me describe the data frame to see the statistics. Now when we describe the statistics, the count, the column, for the column age, the count is 100 data points, mean is 39.6, standard deviation is 5.89, the minimum value 25 percentile, so that means 25 percentage of the data points is has an age of 34, below 34, and so on, and we have the maximum value as well. So we must have seen so many YouTubers just doing this df describe and say we got a perfectly aligned data here, but by that means what are they looking at? What should we be interpreting from this data? That's what we are going to understand, the statistics behind this pandas data frame. For that one, we'll just do some mathematics. Now I will show you the mathematics behind this one. Imagine I have 3 data points, let's say 10, 20, and 30. So if you were to calculate the mean of this one, the mean will be, which is represented by this symbol mu here, which is add all the data points together and divided by the number of data points we have. So it will be 10 plus 20 plus 30 divided by 3, because we have 3 data points. Then this will be equal to 60 divided by 3, which is 20. So that's our mean or average. Cool. Now let's see how we can calculate the standard deviation. The standard deviation is represented by this symbol here, sigma, which is, there is a formula for this one, which is sigma I is equal to 1 to n xi minus mu whole square whole divided by n, and this whole thing will be a square root. So this is the formula for standard deviation. So basically what it means is, for the data points, n number of data points, as I is equal to 1 to n, take every data point here, in this case 10, 20, 30, subtract the mean from those data points, square them independently, add them all together, and divided by the number of data points. So in order to do this one, this will be, a first data point is 10, take away the mu is 20 whole square, plus 20 take away 20 whole square plus 30 take away 20 whole square whole divided by the number of data points, which is 3, and we have to take a square root of this one. So this will be 10 take away 20 is negative 10 square plus this becomes 0, and this will be 10 square over 3. Again, we have our standard square root here. So this will be 200 over 3, which will be square root of 66.66, just goes, and the square root of 66.66 is going to be 8.16. This is the standard deviation. So one might question, why are we squaring these values? It is because the negative values will not negate the positive values. So without the square root, what happens here is, I'm just writing a small example here. So without square root, our first data point will be 10 take away 20, then it will be 20 take away 20, and then it will be 30 take away 20 whole divided by 3. So this will be negative 10 plus 0 plus 10 divided by 3. If you see here, this negative 10 has actually negated the positive 10, which is making it 0, which is the last thing we want to happen. Our whole standard deviation became 0 before because of this one. That's the reason we have to square the sum of individual values, so these negative values will turn into positive values. Because we are squaring this, we are using a square root for this one. Hope that is clear so far. Right. So in probability, so let's move this a bit up here. So in probability, there is the data, sorry, not in probability, in statistics, we have the data distribution like this. This is called a bell curve or a normal distribution. Normal distribution. So when there is normal distribution, you have a graph like this. When your graph looks something like this, more tail on the right side, then this is called a right skew. So this is not a normal distribution anymore. This is called a right skew. And when your graph looks like this means it is left skew. What this means in data point of view is you have outliers on the right side here, whereas you have outliers on the left side here. So outliers are basically extreme data points. Those data points can be more than the optimal value or less than the optimal value. These are the outliers. So how can we use these statistics to detect the outliers here? So there is a general rule in statistics, which is 68, 95, 99.7% rule. So when in this normal distribution, your mean is hanging over here. That's your mean. And the standard deviation will tell you the data points that are varying, how much they are varying from the standard deviation, from the mean. So if you add this mean, our mean is 20 here, and our standard deviation is 8.616 as we have seen here. So if we add standard deviation to this one, this will become 28.16, and if you add the standard deviation one more time, it will be 36.32, and if you add another standard deviation here, it will be 44.48. Similarly, if you subtract the standard deviation from the mean, the first point we get is 11.84. If you subtract the standard deviation again, we get 3.68 here, and then the standard, the last standard deviation will be negative 4.48. So how does this rule apply to this distribution is basically the 68%. This is the standard deviation. Let's write those labels. This is one standard deviation, this is two standard deviation, this is 3 standard deviation. Similarly, this is -1 standard deviation, -2 standard deviation, and -3 standard deviation. So what this says is 68% of your data points, you will find it within this ±1 standard deviation, and 95% of the data, you will find it within ±2 standard deviation, and 99.7% of the data, you will find in this ±negative standard deviation. So 68% of the data will be within ±1 standard deviation, 95% of the data will be ±2 standard deviation, and 99.7% of the data will be in ±3 standard deviation. So any data points after this point, after 3 standard deviation, or any data points below the standard deviation, so we can call this as a lower limit for our comfort, and we will call this as the upper limit. So any data points beyond this upper limit, they are our potential outliers, and any data points below this lower limit are also our potential outliers. So if you understand this properly, what we are doing is we are taking the mean, which is mu, and multiply that with add that to 3 standard deviation. That is your upper limit. So when you do this one, this should be less than the maximum value. And similarly, if you take the mean mu and subtract the 3 standard deviation, then the resulting value should be more than the minimum value. If these two doesn't happen, then you have potential outliers. So now if we go back to our Python, where we have this data frame statistics here, the mean is 39.16 and the standard deviation is 5.89. So 5.89 times 3 is about 17.4, and add that 17.4 to 39. Let's do that in Python for a better understanding of this one. So we want to do data frame of age dot mean plus 3 times data frame of age dot standard deviation. That's df. So that is 57.30. This is less than the maximum value. So that is less than the maximum value. So we don't have any outliers in this one. And similarly, if I copy the same thing and put it here, which is our lower limit, if I take the mean and subtract 3 times of standard deviation, I get a value 31. And we also said that it should be less than the maximum value. It should be greater than the minimum value, which is not. Right. Where does it go? So there is a small problem with the formula I have written here. It should be, the minimum value should be greater than. So I just flip this around. So minimum value should be greater than the mean, take away 3 times the standard deviation, then you don't have any outliers. That's the gist of it. That's how you should interpret this statistics. Now what I will do is I will just add a new data point which is more than this one. Let's say here data is equal to np dot append. I will append the data and another data point called 90. Now let's all run all these cells, and if you see the df describe 3 times 7, multiply the standard deviation with 3 times 7. Okay, our maximum upper limit is 57, but our maximum value is 90, so there is definitely an outlier. We can prove that point by using a hist plot, and I can say data is equal to data, and then kd is equal to true, so we can see that line here. Let's run this. So like I said, it is right skewed, so there is an outlier. Now if I remove this data point here and draw the histogram again, see there are no tails on the either side of the world. So this is a properly distributed data. So you will not always get a proper bell curve here, but it is perfectly fine not getting a proper bell curve as long as your data points are normally distributed within the ranges. So if I add another data point, let's say the age of 1, let's do the mathematics again here for the minimum value. So 6.8 times 3 is about 20. 39 take away 20 is 19. So coming back to our formula here, we said that 19 should be less than the minimum value. The minimum value is 1, which is not. So 18.67 is not less than 1. So we have an outlier. We can prove that by doing this one here. Now we have a tail, huge tail on the left side. That means our data is left skewed. I hope this video helped you. That's it for now. I will see you guys in the next video. Thank you.